only. In case of priority listing method, if there were n units, 2 raised to n decisions minus 1, which refers to the first one, you need to initiate the discussion. So due to that exhaustive number of combinations, the decision need to be taken carefully and it is very lengthy in process. In case of dynamic programming method, if there are 4 units, number of decisions left with you are only 4. So only 4 or n number of decisions are to be taken as per the case yesterday we have discussed. Then the definition was like that, like in case of any system where a decision like a series of decisions to be taken in a process where optimality is to be considered. The statement was like this. It states that an optimal policy has a property that whatever is the initial stage and initial decisions are, the remaining decisions must constitute optimality with regard to the output obtained from the previous decision. In that perspective, I was giving an example, a 3-stage or a 4-stage industrial process till it gets back to the final product, raw material to the stage 1, whatever is the decision taken at the stage number 1. Look to the output obtained from that. And that output is the input to the stage number 2. Decision 1 has been taken off. There is no correction required because output from stage 1 has come already. You are left with a remaining decision to be taken, suppose the 4-point decision, 4-stage decision. Decisions at stage number 2 can be better than the normal what you would have taken. So that output obtained from the first decision, which was not accepted decision at that time, or decision on compromise has happened, and output what is obtained, on that output, you take a decision at stage number 2 so that it is processable and good for the stage number 3 input. In that, stage 2 becomes very interesting and important fact where decision is awaited. Likewise, when it comes to the stage number 3, whatever is the output, whatever is the initial stage, it is stage number 2, the remaining decision left were 3 and 4 like that. There you must see good decisions be taken on the output obtained from the previous decision. In that way, sequential decision need to be taken. So in that way it is applicable. Then we thought this to be applied to a power system. Then how it will do? Let us take a simple case. Like I have a power system. Let right here. Let n be number of systems, number of generators like that. It means I need to check number of machines in the system is n, which have to meet the demand PD. That is, let PD be the demand. Means net demand on the power system is PD megawatt. Ultimately, my target is to see to it that generator 1 plus 2 plus 3 plus 4 plus n, if I combine all these together should produce a megawatt which is equal to PD. That's my requirement. Then I can write, therefore, PD must be equal to summation I equal to 1 to n PGI. An example. It means total megawatt what I obtain from generator 1 plus 2 plus 3 plus 4 till the last unit, last system or generator. If I take PG1 plus PG2 plus PG3 plus PGN should be equal to PD. That's what is the case study. So this is the situation. Then using dynamic programming method, using dynamic programming, running. How it can be written? Total demand PD is such a way taken. Among the n generator available, take first decision such that the lowest cost of production from the n generator you identify, which is that machine which produces output which is lowest among the possible n generator. That means take first decision such that one of the machine you pick as your reference, which is able to produce best output megawatt at very lowest cost of production. Then remaining machines, let's say there are n machines, let us take the last machine, n is my choice. It can be any machine in the string. It is called as whatever is the initial decision, whatever is the result obtained from that decision. Remaining decision must constitute optimal policy with regard to the output obtained from the previous. In that regard, even I did not check the best machine among the n. Simply I should take a decision 1, first stage optimization, get the production cost from that. When the next decision is awaited, take a decision which makes optimal such that your choice is best on the output obtained from the first stage, like that. In that regard, initial decision is simply a mere initial decision. It need not be the best output also. Therefore, let us assume nth machine, last machine I pick up as my choice. Then let us say Pn is the megawatt I obtain from that, like a Pgn what I would call here. Then Pn plus sum of production from remaining machines 1 to n minus 1 machine. Out of the n, the last machine if I take out as my first decision, remaining machines in the string are n minus 1. From those n minus 1, it is the combination. Among the n minus 1, which is best, which is average, which is costlier, I can calculate and I can make a comparison. I will write this demand PD as split. Let this PD be sum of all the productions from the generator. While making my combination from the generator perspective, I will take first decision. Let my nth generator be my reference. Let it produce Pn megawatt, whose production cost also I know as Fn Pn per megawatt, like that. Let me write it and show you. Then Fn bracket summation I equal to 1 to n Pgi. I can write a term Fn, capital Fn, for notice. Inside the bracket, I have sum of production from all the generator till n. It's called total production cost for the PD megawatt, because this total megawatt is nothing but PD as per my requirement. Then what is that investment I will be doing in producing this megawatt is Fn total production cost for these megawatt. I can write it. Then I said this megawatt I will split as 2 parts. The part 1 is like this. This is Fn Pn megawatt summation I equal to 1 to n minus 1 Pgi, something like that. What is the meaning of this? Total production cost for generator 1 to n in meeting PD be Fn of this expression. Now I am on a stage number 1. What I will do? I will split this total production as among the n minus 1, among the n generator, one of the generator I take as my first decision. Let it be nth machine, let it produce Pn megawatt. Remaining machine be sum up to meet my requirement as a PD. The same equation I am rewriting as a two-part. When I write it, again total production cost I know. Now what I will write? As I took a decision number 1. What was my decision? Among the n generators, let my last machine be my first choice. How I took a choice? I took a choice either by merit, which is least in producing megawatt, or simply a choice, because it's my mere first choice. Assume that you have taken a best choice and whose production cost you are able to calculate. Then I can write this as this way. Fn Pn plus Fn minus 1 summation I equal to 1 to n minus 1 Pgi. What is this I wrote? Therefore I wrote the total production cost of PD from n machine, as it got split into two parts: production from nth machine Pn megawatt, production from remaining machine Pgi summation I1 to n minus 1. Fn being total production cost. When I take this machine as my first decision, whose production cost may be your choice? Maybe best machine, maybe worst machine. It is mere choice of yours. Whose production cost you know. Then this expression written as lowercase Fn Pn means you produce n units P megawatt, Pn nothing but megawatt obtained from nth machine, whose production cost you know, or it may be a best machine of your choice, plus Fn minus 1. Remaining n minus 1 machines of this calculation should be inside this string of summation. I have to pick it up such that if I rewrite it, I can write. So I can write other side as I can write here where Pn is equal to output from nth unit. Then Fn Pn is cost of production. Then remaining we have summation Pgi I equal to 1 to n minus 1 is sum of production from remaining machines. Let me write. Then even I can write cost also. What was the cost? Fn minus 1 bracket summation I equal to 1 to n minus 1 Pgr is cost of production from remaining machines. That is just whatever I am pronouncing over here, same thing I am writing. Pn is the megawatt from nth unit, Fn Pn is the cost of production. Summation Pgi I1 to n minus 3 sum of the production from remaining unit, whose cost is Fn n minus 1. Now you have to identify two notices. Lowercase f I used, uppercase f I used. Lowercase f when I used, it is that whose production cost I know as my best choice. And Fn n minus 1 capital which I wrote, still in the string I have to find out the best out of that. Hence this is a discrimination. Lowercase f, uppercase f, just to say decision has been taken whose best production cost you know, which is Fn. Nothing but any unit whose lowercase denotes you have already taken a decision. Fn minus 1 is awaited from the string available combination. You are yet to take a decision in that perspective. Therefore, I mention all these things. Then what must go for you later? the total production cost of producing PD megawatt by this kind of split production from different units should be our minimum. I write at the end. Therefore, Fn, Pn and Pn n minus 1 units should be our minimum. In that regard, I have. Therefore, I write here, obtain the minimal cost of production for the megawatt PD from all these generators be like this. Obtain Fn. Let me write here. Fn summation I equal to 1 to n PGI equal to obtain and hence I write here. Obtain and hence total production cost for n units in this way for the demand PD is equal to, I write this, minima of, min of, you can see here, minima of, what's the term here? Fn for machine, Fn Pn plus summation, sorry, Fn minus 1 summation I equal to n minus 1 PGI. What I wrote here? This is the conclusion. I should see to it that total production cost of PGI from all the n units to meet the demand PD should be minima. I write one of the brackets here. Minima, very minimal from the number of terms when I expand it. When I take it, it will be very minimal by value. What is that? You have taken a decision number 1. First decision output. Suppose n equal to 4. Imagine example n equal to 4. Let me write here. Example. You have taken one decision, which is one of the 4 machines is economic. You took a decision. In this section, you are left with only 3 components. Total example 4 units. One of the units among the 4, you took it out as your first decision. How many decisions are left with you to be taken further? Remaining are 3. Of the 3 which are put in the summation, which is the combination of production of certain megawatt from remaining generator 1. Remaining. When I expand, I will be having combination of those things. So, 1 unit alone to meet, this is the only decision. Suppose you want to combine the decision to be, demand to be met by only 2 generators. Then what is your decision to be taken? Decision 1, and among the string possible, 1 more machine you have to pick. That's the end of the decision. Suppose you are left with the 3 decisions to be taken, 3 machines to be combined to meet the demand, take 1 decision. From these string of expansion, take 2 more decisions, which are very cost effective and cheaper. In that regard, this term which I am speaking about, production cost from n minus 1 unit, summation I n minus 1 PGI has to be expanded. How many terms appear over there in the summation block is n minus 1. In that regard, for a machine example, when I took machine number 1 of the machine I took as a first decision, I am left with the 3 units. I have only 3 terms inside the combination. Like that, I have to check which combination work out for my requirement, like that. So this is clearly understood when I solve a problem. In that perspective, what I am mentioning over here, total production cost of summation I1 to n PGI for meeting the demand PD be taken such that the combination of generators of your string, what you have, such that 1 decision to be taken, bring out the best possible low cost machine which produces the megawatt as your decision. Suppose you are given a chance to take two decisions. Two units have to combine and work for this. Then you are definitely left with the first decision is to, among the units, take a decision which is cost effective first. Remaining n minus 1 units which are there, what is that best among the remaining to be combined with the first decision what you have taken, you have to pick. Suppose you are said to take three machines as your concept. Three machines have to be paired. Then what is your decision? Take first machine as any one machine as your initial decision. Then remaining in the summation block, take two more decisions to combine your total decisions of 3 as per the dynamic programming method. You have to combine for the load. In that regard, the final conclusion is for n machine system, demand is to be addressed by PGI. Total demand production cost is put as production cost like this. Then it is obtained as your minima of these two terms. I am quite sure this will be understood only by a simple problem. Let's take a simple problem. Let me write on this case. When I write a simple example, a two-line example, let us try to apply this case over there. How dynamic kind of programming is put on those generators to find out which is the effective combination of generator for a demand. So it is called as obtaining minimal combination of generator in the mind. So for that, what I will do, I will just take a simple example. That example should clear this derivation. This is a short derivation. Okay. I have a machine. Example, C1 equal to 0.8 P1 square plus 0.25 P1. And I have C2 equal to, let me write here only, I can use some space. C2 equal to 1.2 P2 square plus 22 P2. You have been given an example. Two machines with the incremental fuel cost. 0.8 P1 square, 25 P1. 1.2 P2 square, 22 P2. For a certain load I have here, for a load of PD. For a load 3 megawatt. For a load 3 megawatt in steps of 1. In steps of 1 megawatt. 1 megawatt obtain schedule using dynamic programming is the question. You have been given two incremental fuel cost expressions. C1 is one term absent in that. Then, how to do it? I have here solution. Let us take one of the machine as your reference. So I take let unit 1 be considered first. Means I consider it. What I will do? F, I will make F on machine number 1 for 3 megawatt. Let me calculate. Or 1 megawatt, whatever I want. I can calculate. I have in my note, let me do 3 first, later I can do. 3, what is this? Production cost for 3 megawatt on machine number 1. What I will be doing? 3 megawatt in this position. In this position, I substitute 3. 0.8, 3 square plus 25 into 3. Let me do. That is called as 0.8 into 3 square plus 25 into 3. What I am getting? I am getting the actual production cost of this from machine number 1 as example. This comes out to be 82.2 for me. Now what I should do like this? I should do F1 for 2 megawatt, F1 for 1 megawatt. I should do it. If I do it here, or I can do it directly on the calculator, whenever I put in the string also I can do. It means 3 megawatt load is to be addressed by these two combinations instead of 1 megawatt. What I can do? I can do 1, 2, 3 or 3, 2, 1. However I can go. Because I wrote it because I had an answer in my reference here. When I wanted to get cost of production for 3 megawatt, I refer this. Similarly, 0.8 into 2 square plus 25 into 2 I should obtain. 0.8 into 1 square plus 25 into 1 I should do it. So these are the production cost of machine number 1 with respect to megawatt 3, megawatt 2, megawatt 1. I expect you to keep these answers for you. Now you got this solution. Now, when the schedule is said to be combined 2 units, as per the requirement, both the units need to be used, then as per the unit, as per the condition, both the generator I must schedule for a megawatt of 3 in steps of 1. So I can take 1 megawatt. What is the combination? How much will be the share of generator 1, generator 2? For a megawatt 2, what will be the loading pattern of generator 1, generator 2? For a megawatt 3, what will be the loading pattern of generator 1 and 2, like that, steps of 1 megawatt. Then, as per the requirement, both the units need to be used, then I have a combination. How can I fulfill 3 megawatt from these two machines? Then I'll be knowing the combination. Let machine 1 deliver 3 megawatt, then machine 2 be 0 megawatt. Let machine 1 be 2 megawatt, this be 1 megawatt. Let this machine be 1 megawatt and this machine be 2 megawatt. Let this machine be producing 0 megawatt and this machine be producing 3 megawatt. This is a combination. How can I do it? Let there be a complete load of 3 megawatt on machine number 1. Then combination control on other side is 0 megawatt. When machine number 1 is delivering 2 megawatt, the remaining megawatt is 1 be from machine number other. Likewise, I have a combination to write it. How I should write it? Let us see this. I write it using this concept. What I was pronouncing here, this concept, I will write how 3 megawatt is written as an expression using this expansion I am trying to mention. Okay, let me put here on the top of this presentation. I keep it as it is, this line. Therefore, I have here production of 3 megawatts from 2 machines, from 2 units is equal to production cost of 3 megawatts from 2 units is equal to minimum. You can say min of what I am writing here. Production cost of total 3 megawatts is a split of production cost. Total production cost of 3 megawatts from 2 units is equal to your minimum, such that this combination I will write. How I write it? Look into this. F1, let it be 3 megawatt plus F2 be 0 megawatt. This is the first combination. F1, which is my first choice. F1 be 3 megawatt plus F2 be 0, comma. The other is F1B 2 megawatt plus F2B 1 megawatt. Next combination, comma, F1B 1 megawatt plus F2B 2 megawatt. Then I have F1B 0 megawatt plus F2B 3 megawatt. This is the combination I have. What I did now? This term, when I took a decision number 1, only one machine has to deal, means this won't be there in the picture, only this one. When I have two machines to be dealt, this is your optimal machine with which one of the remaining has to come. But I have only two machines. I have only machine 1, machine 2. Then I'll be having 1, 2, 3, 4. 2 raised to 2 means only 4 combination. How that 4 combination can meet your 3 megawatt load? Like this. Let machine 1 be delivering entire 3 megawatt. Machine 2 be 0. 3 plus 0, demand is 3. 2 plus 1, demand is 3. 1 plus 2, demand is 3. 0 plus 3, demand is the address. But here, one of the machine you took as your initial decision, on which you kept on changing the production like this. 3 megawatt, 2 megawatt, 1 megawatt, etc. Likewise, machine 2 when I consider, I should calculate for 1 megawatt, how much is the production cost. For 2 megawatt, what is the production cost. For 3 megawatt, what is the production cost. For 0, definitely it goes 0. So those things in the respective positions I have to enter. When I place them, numerically find the conclusive value. And among those values, what I'll get now? Here I'll get one number which represents this production cost. Another number, this production cost. Another number, another number. I'll get 4 numbers which represent the production cost of that combination. Among the 4 numbers in a set, elements in a set, find out the least among them. That is your minimal combination product or production cost. Then you have to find out that is the only combination can meet your requirement effectively. In that regard, what I will be doing, this will be equal to in off. Okay? Even what I said, I can do this way, or this calculation I can do right in the position in the same slot. I can do it, I can use, or I can keep it ready, I can use it. So therefore, I have the answer in this way. 0, this one I have 82.2 plus 0. The second term is 0, comma. The second term, this one, what is the value I have? 53.2 plus 23.2, comma. The next one is 48.8 plus 25.8. The last answer is 76.0, whatever the value I have here. It means I should be careful. 82.2. Then I have 53.2. Yes. I have 25 point, what is this? 25.8 and 0. Okay. So it means you respectively F1. So let me write reverse. These two I'll exchange. It will be convenient. 0 plus 76.68. Because I consider first. Because F1 0 means 0. I should be convenient with you. Now when I minimize this term is equal to minima of 82.2 first term. The second term I think gets computed as 76.4. The third term 74.6. The fourth term leads to 76.8. So the total production cost from C1 and C2 with this kind of input and justification shall go in this regard. So I can write now This can be 53.2. This can be 48 point, because I have already calculated 1, 2, 3. 3, 2, 1. These costs are required for me over here, which I wrote here. Then this I'll take off. So I should find out minimum of these two combinations. I have combinations already obtained. Now I'll pick what is the best here. To do that, what I will do, just I'll find out the value which is comparatively minimum. I think this fits here. 74.6. The dynamic programming consists of 2 units for a certain load of 3 megawatts using these 2 machines in sets of 1 megawatt by rearranging in the function minimal production cost for 3 megawatts from these 2 machines from 4 combinations refers to be 74.6. Then the 74.6 to be the minimum. What is the combination or what is that share of machine 1, machine 2? Now I should go. This corresponds to third one, this one. This corresponds to 1, 2, 3, this step. What is this? This say it means produce how much? 1 megawatt from unit 1 and 2 megawatt from unit 2. The dynamic programming method has given you a conclusive state for these 2 machines for 3 megawatt kind of approach. You will get a combination, and from that combination minimal possible number is 74.6. This 74.6, when I go reverse, give me a combination 1 megawatt from machine number 1 and 2 megawatt from machine number 2. When I combine, the total production cost is ever minimum. Then this is another way of viewing the economic scheduling using under the unit commitment schedule by dynamic programming method. Now, how many decisions you took here now? You can just come back. Number of decisions to be taken as number of units here, 2 units. So take 2 decisions. The first decision was like this. 3 megawatt, 0 megawatt. Or 2 megawatt, 1 megawatt. 1 megawatt, 2 megawatt. Or 0 megawatt, 3 megawatt. From this, one of the machine you have to pick as your reference. When you pick a machine 1 as your reference, let us say you took as 1 megawatt from unit 1. What is remaining? Another unit is only 2 units. How much megawatt? 1 has gone, remaining must be 2 only. It means to say, number of decisions have simply got reduced by this way. It is called as taking first priority. Suppose you have to take 2 decisions. Priority decision number 1, solution is complete. Priority decision number 2, that's the end of the solution. If you have 4 machines, you are given with the 4 decisions. First decision is priority number 1. 2 machines have to combine. Machine 1 is already a priority. One from the remaining 3 have to combine as a decision 2. This is priority 1, priority 2. Suppose 3 units have to be combined. First, already you have decided one of the unit as your master unit as a reference, priority 1 plus priority 2 plus priority 3. Done. The last priority, 4th machine. Whenever you are supposed to combine all the 4 generators to meet the demand, priority number 1 is the first attempt. Priority number 2 combined with that. Priority number 3 combined with that. Priority number 4 combined with that. How many decisions you took? Only 4. First decision was identifying the best among the remaining. Means among the 4, what is best? That is priority number 1. Decision number 1 has gone. And remaining 3, which one is best? Pick and combine with the 1. That is your priority number 2. Second decision is exhausted. And it is not sufficient to meet the load. You are left with 2 units, which still you have to take 2 decisions. Take among the 2 which is best. Combine with the remaining 2. First decision output Second decision output, combine the one which have taken decision. So 3 decisions have been completed. Maybe it will suffice your load, or if it will not suffice your load, add the remaining. So how many combinations you took? Only 4 in case of unit number 4 unit problem. Suppose if you would have solved this problem using priority listing method, exhaustive enumeration, 2 raised to n minus 1, it is 2 raised to 4 minus 1, 15 combination you have to check. 15 combination you have to check, 2 raised to n minus 1, that is taken out. Only n decisions you have to take, that's all. That's how the dimensionality of the problem has just come down to the n. Instead of 2 raised to n minus 1 decision, dynamic programming transforms the problem width into n only. Hence, it is the very simplest way of solving the problem. So, please look into this. What I have done is, I repeat back, such a problem you may expect in the examinations or even in the internal assessment test, which we are likely to take off. 2 fuel cost functions are given to you for a certain load in steps of certain megawatt. Obtain schedule using dynamic programming method would be the general statement. Then you have to take for the demand of certain value from machine number 1. For that megawatt in steps of 1, I took 1. What is the cost of production? Substitute 1, get this. Substitute 2, get this. Substitute 3, get this. Keep ready. Side by side if you want, put a line. For machine number 2, for 1 megawatt, what is the value? Machine number 2, 2 megawatt, what is the value? Machine number 3, what is the value? You can keep like this, F1 3, F2 2, F1 1. You can write here F2 3, F2 2, F2 1 equal to what? Like this, you can keep side by side calculation. Nothing wrong in that. You can keep it computed using this equation, 1.2 into 3 square plus 22 3. You can write here, calculate it, you know the answer. What is the answer for that? 76. You can see this answer is 3 megawatt. When this machine is producing 3 megawatt, 3 square in this expression if I put, what I am going to get for this position, answer is 76.8. When this machine is producing 2 megawatt, then you know the 2 megawatt combination, when is it? Here. 2 megawatt means it is 25.8 output. 48.8 is first machine. Second is 25.8. When this machine is producing 1 megawatt, you can just come down here when it is 1 in this 23 point. You can definitely see the second term 0, 23.2, 25.8, 76.8 are the production costs of machine number 2 respectively for a megawatt. Therefore, like this, you can calculate these also. But I have shown you one. The second one I have done here only directly by making you notice F1 3 I have done. Then for F2 0 0, F1 2 I have done. F2 of 1 in this equation 1 square 1. If I calculate it, I would get the answer. That was written here 23.2. If I wanted to do like this, you would have done side by side. Please do it. Nothing wrong in that. Because it clearly gives you the number over here, those numbers, production cost values, you can place in a particular slot. You can get into, and when I make this complete expansion, I'll be having the decision, the final conclusion, obtain minimal of the string which is possible. Then number you pick it up, then go back with combination, fulfill that, write it. That's the end of dynamic programming concept. So when you refer, this will be easier. In books I have, suppose load is changing in step 3 megawatt higher, then how we should write it? I have one combination. Let me write it here. Suppose if I take it out, as the load changes, a number of units are given to you. How to write it? Like this. Suppose I have an example. Another example. So load range. Let me write it here. One parameter. Suppose I have a machine, units. Suppose I have like 1, 2, 3, 4. Let's say I have 4 units with me. Load range, maybe example 1 to 5, maybe 6 to 12, 13 to 17, 18 to 25, maybe megawatt. I mean it, megawatt load range. For example, then number of units what you have is 1, 2, 3, 4. 4 units have to be taken for such a load. Load megawatt may be 1 to 5, maybe 6 to 12, increase to 13 to 17, increase to 18 to 20. A sample example, arbitrary example. There is no real time data which I have collected and explaining you. It is just a conventional mechanism I am trying to convey. May this 1 to 5 load be met by this? I make it possible. These I will not use. I have entry. Machine 1 be used. Active 1 to 5 range. 1 megawatt, it may fulfill. 2 megawatt, it may fulfill. Up to 5 megawatt, it may fulfill. Let's an example. Because I am not giving a scale cost function. I am giving you an example how would the dynamic program be combined for several units for different slabs of load. Suppose 6 to 12, machine 1 may not be able to perform. Then what I will do? Machine 1 along with machine 2 I will load. I will not use these two. What is that? For a range of 6 to 12 megawatt, I may be using 1 and 2. This may be 1, 1. I make active, active, deactive. If the load is 13 to 12, 17 megawatt, for example, these two machines cannot fulfill this range. I may require 1, 1, 1, 0. What I am doing now? All the 3 machines I am picking to meet this demand. Certain example. Then when the load is increasing from 17 megawatt till further, may these 3 are insufficient, I load all the 4 machines. What is this? This is a simple pattern. For a certain slab of load range, one of the units may be functioning. As the load keep on increasing, kept on changing its numerical demand, definitely another unit I need to combine. May I have shown you in an incremental. Best machine, cost effective, the most cost effective, it will inferior, most inferior you can imagine. So I'll pick this because this is my best machine or my first decision. I'll pick this is the best among the 3. I pick